everyone. Today we want to start fluid mechanics course. You may know this course is very important for most engineering branch and also science branches, and of course for bioengineering students. So let's go with fluid mechanics. In this course we will learn an introduction and basic concepts of fluid mechanics. Okay, we can divide fluid mechanics into different sub-branch, fluid statics and fluid dynamics, as you can see here. What is fluid statics? Fluid statics is dealing with the flow of fluids that are at rest, and fluid dynamics is kind of a study that deals with fluids that are in motion. Okay, now it's time to answer to this question, that what is a fluid? From a physics course at the university or in high school, we know that a substance has 3 different phases, right? Here you can see solid, liquid, and gas phase. Also, there is another phase at high temperatures. Here it is called plasma. However, here we do not want to consider this phase. So in solids, we know that the distance between molecules are fixed due to the strong intermolecular forces. However, in the case of liquids or gas, these intermolecular forces are not very strong, and molecules can move from one point to another, and especially in the case of gases, as you can see here, this motion of molecules are completely in random manner. Here in this course in fluid mechanics, when we talk about fluid, we actually talk about this phase, or liquid and gas phase. Okay, before coming to some definitions of and some concepts for fluid mechanics, let's learn some application for fluid mechanics. We, as bioengineers, you know, here we like to study a human body and biological systems. So one of the most important and unique application of fluid mechanics is in designing artificial heart, or in the measurement of pressure in our body, or there are other applications for fluid mechanics in different areas. For example, in natural flows and weather, in the designing of boats and ships, and so on. Here you can see in this slide, for example, in the designing of aircraft and spacecraft, or oil and gas industry, automotive industry, or in the producing clean energy from wind turbines. Okay, let's continue with fluid mechanics concept. You may face in fluid mechanics with different flow classification. One of them is viscous versus inviscid regions of flow. We know that when in solid body, when one solid body move over other solid body, here a friction force develops at the interface of these solid bodies, and here the opposition of this force is completely, the direction of this force is completely in the opposition direction. The same is true for the motion of fluid over the solid surface. Here once again Here, once again, if this friction force develops at the opposite direction, and also when fluid layer move other fluid layer, in this case, once again, this friction forces develops, and we call these friction forces as a viscosity, which is a property of the fluid. Here, we know that this property is due to the resistance against the flow of that fluid. Okay, in this figure on the right, as you can see here, we know we see the flow of one fluid over a flat plate. Okay, in this kind of flows, there are some different regions, viscous flow regions and inviscid flow regions. Some parts that are called inviscid flow, in these regions, viscous forces can be negligible because in these regions, pressure forces or inertial forces are more strong and are dominant. That's why in these regions we can consider this flow as an inviscid flow. However, in the intermediate part of the flow, here viscous forces are more dominant. Okay, let's continue with another classification of flow. It is internal versus external flow. When a flow of a fluid confined between layers or boundaries, we can consider that flow as an internal flow. For example, the flow of water inside a pipe can be considered as an internal flow. However, for the case of flow that is not confined and the flow is over a surface, we can consider in this case as an external flow. In this figure on the right, you can see the flow of a fluid over a tennis ball, which is considered as an external flow example. Okay, in this slide, I have summarized the difference between external flow and internal flow. As in the case of external flow, as you can see here, flow enters over a surface. However, in the case of internal flow, there is a boundaries here, as you can see here, two boundaries for the flow of fluid inside a pipe. So we call this flow as an internal flow. Another classification for flow that we face in fluid mechanics is compressible and incompressible flow. Here in this figure, let's consider two fluids with volume 1 or V1 that is under pressure P1. Then we increase the pressure from P1 to P2, right? As you can see here, the volume changes by increasing the pressure. So we call this fluid as a compressible fluid. However, there are some fluids, when we increase the pressure or when we change the pressure, we will not see any change in the pressure. That's why we call this kind of fluids as an incompressible fluids. We know that the gases are highly compressible fluids, and liquids can be considered as an incompressible fluid. Okay, another classification that we face in fluid mechanics is laminar and turbulent flow. Then, what is laminar flow? Let's answer to this question. Laminar flow is actually a kind of flow that in this flow particles of fluid pass through a straight line and parallel to the boundary of the flow, and it is completely orderly flow. However, in the case of turbulent flow, there is a mixing matter here, and here these particles from layer to the other layer can easily move from one layer to another layer, and these particles are moving in a very chaotic and very disordered manner. Okay, this is an experiment that for the first time Reynolds conducted this example. Here you can see a pipe. Reynolds first injected a dye to this pipe, as you can see here with red line. As you can see here, for the case of laminar flow, these particles completely flow in straight line and in parallel with the boundary. In the case of turbulent flow, as you can see here, there's a mixing between particles from different layers. And also there is the transitional flow, which is an alternating between a laminar flow and turbulent flow. Okay, this is the Reynolds number that Reynolds for the first time developed this equation to characterize the behavior of flow. And Reynolds noticed that for the Reynolds number higher than 4,000, this flow can be considered as a turbulent flow. If the Reynolds number is between 2,300 and 4,000, it is a transitional flow, and in the case of a Reynolds number less than 2,300, we can consider that flow as a laminar flow. Okay, this is another classification of flow that we usually overcome in fluid mechanics. It is steady versus unsteady flow. What is steady and unsteady state flow? We in some flows we notice that parameters change with time for that flow. However, for some flows, these parameters remain constant during that course of time. Okay, this is a summarization of a steady and unsteady state flow. For example, in this type of flow, which is called steady flow, as you can see here, the flow of a fluid inside a pipe. As you can see here, the velocity is fully developed. We can see that here the velocity or average velocity does not change with time. In the case of unsteady state flow here, as you can see here, the flow of water from a reservoir, the velocity will change with time. And there is another flow, it is called quasi-steady state flow. This flow behavior will change with time, and however its change is kind of oscillation with time. So that's why we call quasi-state flow. And one of the classification of flows is about its dimensional aspect. Here in this example, we can see a flow of one fluid over this pipe, inside this pipe. In this region, in this red line, I mean, is the entrance region, okay? As you can see here, the velocity will change in Z direction and also in R direction. After the velocity that is fully developed, after this point, as you can see here, the velocity will change only in radial or in R direction. So we call for distance the flow as a two-dimensional, for this one as one-dimensional. Or the flow of a fluid in this pipe, for example, which is fully developed velocity profile here, it is one-dimensional for this case, that flow of a fluid inside a duct with different distances, it is called two-dimensional flow. Okay, now we know the different types of flow. Let's continue with the property of the flows. One of the properties is density, and we know its definition. It is defined as mass per unit volume. We know the density of gas is proportional to pressure, and it is changed inversely with temperature. However, for the case of liquids, this property does not change with pressure. That's why we call liquids as an incompressible substance. Or another property that we face in fluid mechanics is specific gravity. We can calculate easily by calculating the density of that fluid with respect to a standard fluid density. Usually it is water at 4 degrees centigrade, and its density is equal to 1,000 kilogram per meter cubic. And this is another property of fluid. It is specific weight, which is weight of a unit volume of a substance. We can easily calculate by knowing the density of that fluid and gravitational acceleration. Okay, now it's time to learn Newton's law of viscosity, but before coming to that term, it is better to review what is normal stress, what is shear stress. From the physics, we know that when a force acting on a surface, as you can see here, this force that acting on area of A will have two different components, tangent to surface and normal to surface. Now we can easily calculate normal stress and shear stress by using these two components. The normal stress is equal to normal component of the force over the surface area of dA, I mean here. If we want to calculate shear stress, we should use this component or tangent component of force to calculate the shear stress that applied on the surface area of A. In this figure that I've put here, we can visualize different types of loading for a solid. You may understand different types of loading for a rod in the case of compression, tension, shear, torsion, and bending. Okay, for the first time in 1687, Newton studied the flow of a fluid between two parallel plates. From the statistics, we know that the shear stress, or tau here, we know that this is the tangent force over that applied on the surface area of A. We can easily calculate this shear stress for a solid, and this shear stress completely is proportional to the strain. However, Newton noticed that for the case of fluids, here once again this is the shear stress and this is the shear force on the surface area of A. He noticed that this shear stress is proportional to strain rate, not the strain. It means that when we apply the shear stress, this fluid will not resist against this shear stress, and it will start to move. Okay, this is the equation that Newton for the first time developed. This is the shear stress, and this is the velocity gradient here, and this is the coefficient of this equation, which is called dynamic viscosity, which is a property for Newtonian's fluid that we will learn in the coming slides. This is the it's a unit kilogram per meter second, or normal Newton second meter square. Okay, in this slide, as I said before, there is a proportion between shear stress and shear rate or rate of deformation for the case of liquids. We can easily calculate the viscosity of a fluid by using these kinds of curves. The slope of this curve will give us the viscosity of that fluid. For example, here this curve will give us the viscosity of air. This is for water, and this is for oil. As you can see here, these are straight lines. And once again here, we know that for the case of liquids, this viscosity decreases with temperature, because when we heat this fluids, the intermolecular forces between these molecules will weaken, and that's why their viscosity will decrease. In the case of gases, due to the collision between the molecules that will increase with increasing the temperature, its viscosity increase here. Okay, here, as I said before, for the fluids, we know that the shear stress is proportional to the shear rate or strain rate. For the case of Newtonian fluids, we can easily calculate the viscosity from this straight line. For the ideal fluid, we know that the viscosity equals to 0. And here, we know that we face actually with some fluids that these fluids, their behavior, I mean, will change with shear rate, but not in a strain line, but in different pattern, as you can see here. This is a power law that presented for these kinds of fluids, that is called non-Newtonian fluids. Here viscosity for non-Newtonian fluids is not a property, because it is changing with shear rate. In each point we will have different viscosity, so that's why we call these fluids as non-Newtonian fluids. Okay, so far we learned dynamic viscosity. Here we can easily calculate this dynamic viscosity. There is another term that we should learn in fluid mechanics. It is kinematic viscosity. We can easily calculate if we have the viscosity of that fluid and the density of that fluid. And its units is meter squared per second in SI system, and there are other units, as you can see here. One thing that we should keep in our mind, we know that here, for example, we have air at 20 degrees centigrade, but at different pressures. As you can see here, their dynamic viscosity remains constant, but their kinematic viscosity will change by changing the pressure. So it is here kinematic viscosity is pressure dependent. Okay, let's continue with surface tension and capillary effect. We want to study a capillary effect and to understand what is capillary effect. To come to that point, we should study surface tension. And what is surface tension? We can easily define surface tension as an energy that is required to increase the surface area of a liquid by a unit of area. But to understand in more detail, here I put in a picture here. This is a molecule that inside the liquid, and this molecule is on the surface of that liquid. We know that for a molecule that is inside the liquid, these forces that is between molecules, the adjacent molecules I mean, are in balance. These intermolecular forces or attractive forces are called cohesive forces here. So in this case, these forces are in balance, okay? However, in this case, as you can see here, there is another phenomenon here. As you can see here, these forces are not in balance due to the attractive forces between the adjacent, and here there is not any other molecule to balance the forces. So here the force is inward to the liquid, okay? However, in this case are in balance. So these forces are called cohesive forces. There is another force, it is called adhesion forces, okay? This force is acting on the surface of liquid and solid. So when adhesive forces are stronger than cohesive forces, in this case molecules of water try to attach to the surface of solid. However, when cohesive forces are stronger than adhesive forces, in this case, as you can see here, these molecules of mercury try to stay far from the solid surface. So when adhesive forces are stronger, it is called wetting fluid. When cohesive forces are stronger than adhesive forces, we call that fluid as a non-wetting fluid. So by using this phenomena, we can actually describe what is capillary effect. Capillary effect, when we put a capillary tube inside two different liquid, here water and mercury, as you can see here, in the case of wetting fluid, this fluid climbs up. In the case of non-wetting fluid, we notice that this fluid comes down. So by using this surface tension phenomena, we can easily calculate the amount of capillary rise for the case of water, or the amount of capillary fall for the case of mercury. Actually, here there is a force balance between the weight force and surface tension forces. Okay, here in this slide we can easily calculate the amount of H, the quantity I mean. There's a force balance. This is the weight of the liquid that is inside this capillary tube. This is the surface tension on the surface of this liquid. It is 2 PR, which is a perimeter of this liquid at this point, times surface tension, times this cosine of this angle, it is phi. So by writing a force balance, this is the weight, which is equals to mass times gravitational acceleration. From there, we can know that the volume of this fluid equals to PR squared times H. So this is the weight force, and this is actually surface tension force. From there, we can easily calculate this H, the amount of rise or the amount of fall for the case of mercury. Also, we can describe by using surface tension how a bubble forms, and by using this surface tension phenomena, actually by using a force balance, we can easily calculate the amount of pressure inside a bubble or inside a droplet. We know that there is air inside a bubble. This air will cause a force, pressure force, that is in this direction, and on the perimeter of this bubble there is a surface tension inside or toward the liquid. Okay, so if we can put this or we can write a force balance for this bubble, this is surface tension, and this is the pressure forces inside this bubble. From there we can easily calculate the pressure difference for that bubble or droplet. Okay, this is the last lecture of this slide, this lecture and this slide. Have a good time, take care of yourself, see you next time, goodbye.